Fine? So, yeah. In the last session, we had anybody's problem. So we finally arrived at molecules. Now it's time to have a closer look how to solve this wave function for molecules. And especially have a closer look at Hartree-Fock theory and the phenomenon of correlation. First thing is getting rid of the spin. So when we consider electrons, we have the spin, we know this. And the eigenvalue can be plus or minus 1/2. And we have corresponding wave functions for either alpha spin, which is up, or beta spin, which is down spin. And the good thing is that spin eigenfunctions are orthonormal. So this works easy. And they're multiplicative with the spatial wave function. So we want to have our wave function with the spatial coordinates and the spin, we just multiply. And this is all we need. So, furthermore, the spin is also multiplicative with itself. So this uses these integrals of our spatial and spin part, and another spatial and spin part, and we see we have an overlap of 1 if both spatial and spin is fitting, and we have an overlap of 0 if it is not. This is pretty deep, and it's good to know. So obviously, spin works as any other wave function, which is nice. Now let us check our integrals from our molecular Hamiltonian. So, in principle, we have several cases. Both with alpha spin, both with beta spin, one with alpha, one with beta, one with beta, one with alpha. So here it's explicitly solved. We have the spatial part, and our Hamiltonian only works on the spatial part. And we have the spin part. So if we have the same spin, both are at alpha spin, we obtain a result. If both are at beta spin, we obtain a result. If spin differs, we get 0, regardless if it's alpha, beta, alpha. Yeah, so we see the one electron operator survives only if the spin is the same on both basis functions, right? Change, have different spins, and our one electron operator is getting 0.
This is for one electron and one proton. Right?
This is the typical for any hydrogen-like system. This is our one electron operator, what we had last week from the full Hamiltonian, right? We had this H plus J minus K, you remember? And so this one electron part for hydrogen-like systems only works if we are with identical spin. Actually, what it means is because Hij is the one electron energy eigenvalue times the integral Ij means that we only obtain a one electron result when both spatial orbital and spin orbital are identical. So we cannot mix different spins with one electron operator, and we cannot mix different spatial orbitals. Both doesn't work. As you can expect from hydrogen, right? Next, our Coulomb operator. Well, okay, the alpha-alpha case, just as we know, and the alpha-beta case, actually also works if they are on the same orbit. So we have orbitals which are sufficient for our one electron operator. We build our basis from them, and we see that the Coulomb operator always survives. Which is nice. So if I has spin alpha and J has spin beta, it still survives. Because we integrate spin alpha in the coordinates of the first one and spin beta in the coordinates of the other one. So obviously this works. And we always keep our Coulomb operator. The exchange operator is a little bit different because it does some exchange. If we have alpha spin here, it doesn't matter. So I alpha gets exchanged with J alpha, still has a 1. But as soon as I and J have different spins, we obtain 0. And this is because of the fact that this operator is an operator that also just works on spatial coordinates. So we move the entire J beta into the first coordinates, right? So all of a sudden we have such an integral, alpha beta beta alpha, which is the same as the alpha beta integral and the beta alpha, and they are both 0. So we have a term times 0 times 0, which is 0. I've told you last week that K is 1/2 and J is full. This is how we have it, right? So we integrate over all possibilities, and this is a full sum of this Coulomb and exchange operator. The good news is this holds for any system with an even number of electrons and the same number of electrons for each spin. Of course, as soon as we change this, when we have more electrons of alpha spin than we have of beta spin, then additional terms come, which survive from here, from this part. Right? So we are not that total. So for each electron in excess of this even distribution, we get a little bit more of this. Now we can work. We have the Fock operator. We've already have seen this last session. And this yields one electron wave functions for n electrons. If we doubly occupy our spatial orbitals, we have n-half orbitals. We integrate over all of spin, we say all are doubly occupied, and we just have to go for n-half. So, with our one electron-like orbitals, but actually they are 2 electron orbitals, because we can doubly occupy. This is this hydrogen-like terms. We obtain 2 times our J operator, because now we just count for n-half. So we have 2 times these, minus Kj, and this yields some nice energy eigenvalues. One thing of Hartree-Fock theory, which I don't have on the slides because I wanted to give you as a homework, is, which is nice, to prove that the full energy of all occupied orbitals is not equal the full sum of, well, actually we have to count till n, 2 times the sum. Okay? It will take some brain to solve this, but it will give you some indication on how this operator works. Now our problem is that we are not dealing with eigenfunctions. We want to vary, we want to find a basis. So for this we need basis functions. So let us say these I are basis functions in a way that they are taken from whatever single atoms, from hydrogen atoms, whatever we have. Then we can expand this basis and obtain with the expansion coefficients an eigenfunction to our system. Right? With this, our equation looks like this here. F is F C times whatever, epsilon C times whatever. So far so nice. Now we introduce an overlap matrix, which is just the overlap of our basis functions, any pair we find. And we obtain this matrix equation. So we have any Fock matrix element in terms of our basis functions. This is our expansion coefficients in a matrix, right? This is our overlap matrix. This is, again, expansion coefficients, and this is the energy, which is diagonal. So what we actually have is Fij is just integral I of j, right? Cij has then just something like all the CIM inside till the end. So just sum over it. Sum over M. Like this. And with these matrices, we can work. Okay, overlap matrix is clear. We have it here. And the energy matrix is diagonal. So what we obtain is a nice matrix equation. We can directly go to linear algebra and solve it. Unfortunately, it is not such so easy. We don't get it immediately. It's iterated. Because after the first iteration, we have our initial positions of electrons, right? Where we have our mean field. But the electrons are now each seen independently. Each one sees all the other initial positions. But the initial positions don't take into account where the electrons are optimally. So how the wave function should really look like. So after the first iteration, we get a better wave function for each electron. And then we put it into the equation again, look at this, how the electrons interact, get a more improved wave function, and so on until we reach convergence. And this is how it works. Very simple algorithm. In the beginning, we need our atomic information. So where are our nuclei? What charge has each nucleus? How many electrons has the entire system? Because we may also charge our system, right? We do not need to have number of nuclear charges equals number of electrons. We can also work with charged systems. And the basis set. Whatever this is. Then we compute all our matrix elements which come directly from the basis set. Right? Then we determine a density matrix with our initial population of our expansion coefficients. Well, this yields a density. If we have if we directly start with eigenfunctions, this density matrix is a unit matrix. We have this part, so we can compute our Fock matrix. We diagonalize, it should be F, so that we get our a new Fock matrix, which is diagonal, which has some kind of eigenvalues, which also yields new coefficients as eigenvectors. From our new coefficients, we compute a new density matrix. And then we compare if the new density minus the previous density is less than the accuracy we desire. If yes, we compute our observables, like expectation values of the electrons, momentum of the system, whatever, pressure, energy, anything we want. Well, okay, energy we actually have gotten. Gradients, second derivatives, whatever. If no, we go to here. Now P prime becomes our new P, is inserted here, we compute F with the new coefficients C, right, and so on. We continue until we converged, which means that we have reached this condition that below the desired accuracy is any change to the density.
I have a question.
Yes.
Does this solution depend on the basis set that we use?
Actually, yes, because each basis set yields a specific accuracy, right?
I was wondering if our basis sets cover the entire space, right? Like if you use, for example, Legendre or whatever thing that actually spans the entire thing, then if we write it in terms of any orthonormal basis set that we have, they're going to at the end yield the same thing, right?
Actually, no.
Okay,
So,
why no?
because first of all, our basis sets are never complete. A complete basis set would include an infinite number of basis functions.
Yes.
So, as we have truncated basis sets, this means that we get an error, which relies on the truncation. And then it depends on how flexible our truncated basis is. If it is very flexible, it can fit. If it is not flexible, it does not fit. And we are getting regardless how good our expansion coefficients get, we will reach a limit where we do not find any better expansion coefficients.
Yes.
And in this case, so yes, this condition is always fulfilled,
Yeah,
but the accuracy in energies
but
is not.
basically, your solution is as good as your basis set.
Yes, have a large basis, have a good solution. Have a very small basis, and you don't have a good solution at all. Yeah.
I have a question about this algorithm. I don't know if previously, every time when you were talking about this fundamental equation, we are dealing with the differentiations.
Yes.
Through this algorithm, I haven't seen any differentiations.
No,
It's
we
kind
haven't.
of an eigenvalue problem, right?
Yes, right.
But I don't know, previous lecture later on, you have transferred from the determination of the solution from differential equation into the eigenvalue problems already?
Yes, yeah, but yes. So we are now in full quantum mechanics. We cannot use our classical Lagrangian or Hamiltonian.
Right.
So
That was
we use it
assumption.
to
Okay,
eigenvalue.
so this one, I know the DFT will be further based on this, right?
Yes.
But this, under what kind of assumption we can transfer the original problem into this case?
Well, only with the assumption that we are working with a quantum system. So we have the boundaries that we have quantum states, and that the quantum states have energies which are eigenvalues to the Schrödinger equation, and the wave functions, or orbitals as we call them here in chemistry, are eigenfunctions.
So I guess what is missing here, it was that for solution of Schrödinger equation for the hydrogen atom, for the particle in a bug, we always solve the partial differential equation, and we
Yes.
Right.
Well, this
suddenly
is
we are seeing that there is there is a magic.
Right.
There is no partial differential equation, and we are solving
Well,
a complex system, right?
Actually, it's
Right.
still there, because this h here is of course minus 1/2 Nepler squared plus v, which is the potential between electrons and nuclei. This is included in this operator.
Oh.
So we still have this, right?
But this can be for many particles, or
This can
many.
be for as many particles as we want. So what we always have is plus v, well, sum overall electrons, nuclei, and z by, sorry, this must be minus, z by r. Yeah? So this is still our differential equation, which we had in the beginning. It is now just in the form of the operator. We do not write it out. It is now just still the operator, nothing else.
And also the step number 5, you are saying the diagonalize E. Is that
and we
the
have-
calculation of eigenvalue?
This is the eigenvalue of the Fock operator.
Right. So calculating or determining the E. So the E is the
Our energy eigenvalue.
right. So the eigenvalue, right? But you rewrite the E with the diagonal
Yes,
components only.
yes, yes.
Okay.
So the cost of this solution is mostly diagonalizing a large matrix.
Yes.
Right?
Yes, and the primary trick is to solve all these integrals only in an initial step. They are stored. So later on we just take our coefficients into the equation. So in principle, when you take this one and put it onto a GPU, you get a very fast solution. Because we are in a purely vectorial problem. So this can extremely speed up everything.
Is there any way to make sure that we are actually choosing the very best basis?
Yes, vary the basis. And extrapolate.
I see.
So make our basis larger and larger, and then extrapolate and see how it fits.
Mhm.
So typically one should also see some exponential relation between basis set size and the energy, which is the only observable we have inside our algorithm. So which is just like this. So in principle, we don't need much. I mean, we have here a certain set of basis functions, and here another set. And we take our points, and then maybe a third one. And from here we can extrapolate, and we can see can determine the point where our basis becomes larger than our desired accuracy demands it. In principle, there's a rule, it doesn't, if computer power wouldn't matter, the larger the basis, the better it would be. But, of course, computer power matters, right? If we don't have fast computers, this is getting us into big trouble if we are just working with, when we can put 1,000 wave functions on a hydrogen atom. That's no problem. But the computer will not will show us that it is a computational problem then.
So I'm still trying to understand the transition because what is the physics behind? So originally we were talking about this kind of a multi-particle system
Yes.
controlled by the differential equation, Schrodinger equation, right? So through this way, we can certainly solve a problem with under some kind of assumption you mentioned. But what is the physics?
The physics is that in principle, we can construct from any sufficient basis, which is not an eigenfunction to the system, we can construct molecular orbitals which are eigenfunctions. This is a general assumption. And the other physics is that in principle we are looking for the optimal mean field of electrons. So this is the problem translated into physics. What is the optimal mean field of electrons?
So then that's h or whatever shape function, wave function. So it's kind of the mean, the average.
Yes.
One.
Yes. So that every electron sees the mean field of all other electrons, so that it least affects this electron, or let's say least negatively affects.
And again, we are trying to find the minimum, right?
We are trying to find a minimum. Yes. And from the variational principle, which is still valid here, we can say for sure that we cannot get below our minimum, not below the real minimum. So it is still a variational approach.
So for example, if we have 10 lithium atoms, so
Yes.
it means that we have 30 coordinates for electrons and 10 coordinates
Yes.
for
Actually, we have even more.
spins.
So in a minimal basis, we would have 30. But we are not in a minimal basis because we are facing another problem. Well, in principle, anything which is somehow fitting to the problem can be a basis. But the original hydrogen-like basis is a little problematic because we have this e to the minus zeta r. You remember? So we have here this cusp. And this cusp is a singularity. It is not continuous. So we do not find analytical derivatives at this point. We do not find analytical integrals at this point. And we have a problem. Well, of course, we can exclude it, but do this for 1,000 atoms, right? Then you have to exclude 1,000 singularities from the integral space. But what we can do is, if we still want to get close to this, we can fit a set of Gaussian functions. So we are calling this hydrogen-like basis a Slater type function. And then we fit it with Gaussians. So you see, I have 3 Gaussians, one very narrow, one in the middle, one pretty flat with different amplitudes. And if we sum them up, we fit to our Slater type function. The good news is we have something which is mathematically much easier to deal with, right? We have always in our integrals some products, and whatever product of two Gaussians is a Gaussian. Integral of a Gaussian is the error function. We immediately have our solutions analytically everywhere. Nice stuff. Speeds up things a lot. Hack them once into code, and you have it. But the problem is, already in this simple example, 3 Gaussians make up for one Slater type function. So, back to the 30 electrons from the lithiums. Now each electron comes with 3 basis functions. Each Gaussian is a basis function. So now we have 90 electrons. So we're not dealing with a 30 times 30 matrix, but with a 90 times 90. Still, only 15 of them are occupied spatial orbitals, W occupied, right? but we have this large amount, this huge matrix to solve.
So it's not the only the number of electrons, so it's the number of the coefficients that you are trying to optimize, right?
Yes.
Wow.
This as well. So we can fit. In principle, we have the coefficients variable. We need to. So this gives a lot of flexibility, and this gives a perfect fit. But this is not totally necessary, because there are some kinds like the inner shells, which do not change much in chemistry. Actually, they do not change at all in most cases, because it's the valence electrons which are reactive. So what we can do is, we have our base of primitive functions, and we can optimize once and keep these coefficients constant for the ones optimized, inner shell orbitals at least. Okay? And then for our subsequent Hartree-Fock, we multiply it with one coefficient. So we have our Hartree-Fock coefficients, our C, let me stay in nomenclature, Cm alpha, working on any kind of alpha, gives our proper Hartree-Fock function. Now, at the same time, alpha is just alpha is then the sum, well, let's call it kappa, call them K alpha I. But we keep these K constant. So we have some inner shell functions which are like one Slater type orbital is described by, say, 15 functions, but it is an inner shell orbital. So these coefficients, K, are once optimized and then kept constant throughout our entire computation. So we still have to evaluate the integrals for these 15 functions. But we do not have to evaluate the coefficients all the time, because they now share one coefficient, which is scaling all of them at once. This reduces work. And little nomenclature, we find this in the description of basis sets. On the left-hand side, you see the primitive Gaussians. And on the right-hand side, you see what is left after contracting them. So what does it mean? We have 10 primitive Gaussians of S-type character. And we make 6 contracted Gaussians out of them, which are still of S-type character, for sure. Yeah, because S is just a constant times the radial part, so times the Gaussian part. 4 p-type functions are contracted into 3 p-type functions. Well, actually what this means, this 4p to 3p, is pretty clear. We take 2 of the coefficients and merge them, so keep them constant, just like this. But the other 2 are still kept variable, right? Otherwise we can't go from 4 to 3. If you would go from 4 to 1, all 4 would become constant and later on was multiplied with a single coefficient. But here, as 3 are left from 4 in the beginning, this means 2 are kept fixed with respect to each other. The remaining 2 are variable. Same with the D. And now with the S, it's typically then an inner shell where 4 S orbitals just are fitted for the inner shell, and all the remaining ones are more or less flexible. finally we have some F. So some abbreviations. The Slater type orbital is an STO. A Gaussian type orbital is typically a GTO. Primitive Gaussians are either PG or PGTO. Generally, Gaussian type orbital is a GTO, and with this you can work. Now the question is, how do we have our SPD and so on? We do not use spherical harmonics in most codes. What instead we do is to simply use easy polynomials. So S is the constant times our Gaussian, right? P is then either x times Gaussian of x, so this would be a px. But py would be y times Gaussian in y direction, but we z the same in z. Easy. Well, you get the idea, right? X squared minus y squared is then x squared gx minus y squared gy and so on. You can construct your d orbitals, but if you construct it in this Cartesian way, you do not get 5 d orbitals, you're getting 6. This means you make it simpler to compute for the price of more computation. But this was okay with P, it's not a problem, but it starts with D. So you have 6 d orbitals, you have 10 f orbitals, and it's getting worse. Just look at the transformations for the spherical harmonics from spherical coordinates to Cartesian coordinates. It saddens the day. But it works. Actually, there are also codes which are then using these transformations and directly go for 5 functions. So this may work. So then you have to multiply angles and then project this on the fly into the Cartesian space. Both is working. The Gaussian software typically is using 6D functions and so on. TurboMold software package is using 5D functions, and the developer of the original TurboMold, Professor Alrichs from Karlsruhe, told me on the summer school, if you're ever using the 6D functions, you deserve capital punishment. It's a question of opinion. But in principle, it's just multiplying some polynomials, and it works. What one also can do is, well, we have a good basis which describes all our orbitals for the atom pretty well. Typically, they're optimized for atoms. Now we want to go for bonds or anything else. What we can do is add more diffuse Gaussian type orbitals when we have strongly excited states, Rydberg states, dispersed interactions, whatever we have. So what we actually do is we have our whatever we fit. So this would be correct. We fit it well, but we need some density far outside. So we're adding such a very, very flat Gaussian function, which works with a diffuse function here. Pretty nice. Works extremely fine. If you want to go for a Rydberg state, which is an electron closely before it leaves the atom or the molecule, you have to use them. if you go into condensed matter and you use them, your simulation crashes because they have such a long range that you can no longer decompose your bases. So be careful with these. And furthermore, we have polarization functions. Well, the polarization function is something, we take a function with higher angular momentum than we actually have in this orbital. And this polarizes. I can show this for an s orbital, which is pretty simple. Our s orbital looks like this, right? It's a sphere. Now, if we have it in something like H2O, we have more density at the oxygen than at the hydrogen, right? If we take these as they are into the computation, we need a larger basis to achieve the same effect. But what we can also do is, just give it just positive, add a p function to it. We just added. So this means that here some density is reduced. And on the other side, we are having more density. Unless we are too high in the amplitude here, we do not induce a new node. So we still stay positive all the time. And this is polarization. This is typically used to work with a much smaller basis than we actually would need. And perhaps I should give you some ideas on basis set nomenclature. So what we are using is we try to have one zeta type. Well, this would be a single zeta basis. But we can also say that in principle, it is not good enough to just describe it like this, but also it gives a better description if we add several zeta type orbitals together. This would be a triple zeta basis. So for each zeta type orbital we are fitting together in it, we say it's another zeta. So this is triple zeta. You find this, for example, in nomenclations like SVP, DVP, TVP. These are typical nomenclations for basis sets. Single zeta, valence bond is polarization. Double zeta, valence bond, polarization. Triple zeta, valence bond, polarization. Right? These are typical names for basis sets. You can also have it with more than one p, then it means some extra polarization functions added. From Popel's group, you have typical names like 321G. What does this mean? This means that the inner shell electrons are described by the contracted Gaussian of 3 Gaussian functions, and the valence is a contracted Gaussian of 2 functions plus a primitive function. This is a double zeta basis. 1 zeta, 2 zeta. G is for Gaussians. If you want to add some polarization, for example of p-type, then you polarize your s-type orbitals, then it's written like this. More known, and what you may find in many papers, 631G. By the way, they also have an abbreviation for this. G star. So, 631G. 6 primitive Gaussians make a contracted Gaussian to describe the inner shell, And you have a double zeta, first zeta by 3 primitive Gaussians, second by 1. All Gaussian. This basis exists also in the variation with additional polarization and in the variation with a plus, which means diffuse functions added. You can get larger basis sets, 6, 3, 1, 1, plus, plus, G, star, star. Okay? Well, why? Because here now you can also polarize even more. So these are some of the famous basis sets, which are pretty nice, pretty usable. But they are all Gaussian types, they all have this G. But we're not limited to Gaussians, are we? So in condensed phase, we have a little problem. We can, of course, work with Gaussians in a condensed phase, but the Gaussian is very localized by nature. So what can we do? Well, of course, you can take many Gaussians, and you can use fast Fourier transformations for the mapping of the multiperiodic images. And the good thing is that the Fourier transform of a Gaussian is still a Gaussian, which is nice. But it still doesn't give us a band structure unless we have really quite a vast amount of Gaussians. So what we can do is go to something unlocalized by nature instead. So what do we have for this? Plane waves, sine or cosine functions in principle. We have a sine function in the propagation direction and a constant in all the other. So it's pretty easy. And with them, you can construct your basis. You know, particle in a box, pretty similar. It's a solution. You get energies. Each one has its own energy. So you define a cutoff when you have enough of them. You say anything beyond this energy is not taken into consideration. Well, interestingly, they also can be localized, but only under periodic conditions. Yeah, you know this nice effect from waves that when you have one sine function and you combine it with a much more oscillating wave function, you have something like a wave packet. Right? And so on. So you have, okay, it's not easy to see here, but in principle what you have here is localizations as well. And they are periodic by nature. So in the condensed phase, this may be a much better idea than using Gaussians. Or you can combine both. Then you have a Gaussian and plane wave spaces, which also works and it's also used. And I mean, these are also functions which are easy to Fourier transform. So, this is what we have. And then we have a little problem in the end. If you permute two electrons, we have a change of sign. Correct? So, how do we form our basis? Well, we have independent coordinates. What you've learned so far, this would mean just multiply all of them and you have a nice solution. Well, the problem is if we permute two electrons and we have a product, we have the constant sign of our function, right? ABC or ACB doesn't matter. It's still the same sign of this. But there's an easy solution. We do not multiply them. We make a determinant out of them. When we have a determinant in the diagonal, we have the straight multiplication. But if we change two rows or two columns of a determinant, we are changing sign. So a determinant solves this problem. And this determinant we call the Slater determinant.
What's the name of the determinant?
Slater determinant. Same guy at the orbital. It was a pretty clever idea because in the original first formulation, Hartree and Fock were using Hartree products, which is just a straight product. And they found out, well, okay, nice solutions, but somehow it doesn't look like fermions. And Slater had this idea of, well, why don't we put it in the determinant then? And it does the job. Unfortunately, we have some disadvantages. So far as we had it, it's a closed shell formalism. So this means any orbital can either have 2 or 0 electrons. So let's go back to hydrogen. If we dissociate, you can have either 0 or 2. But obviously that's not the dissociation, right? And we directly see it in the curve for this. Yeah, because then we are having what we would expect is a harmonic oscillator. When we're getting too close, we're getting repulsion. And when we're going to infinity, we're getting a constant. What our Hartree-Fock gives us, however, is this, and it goes here forever. When we go to infinity, we just get infinite energy. Sure, it doesn't dissociate correctly. Okay, let's try to solve this problem. Let's say we just do not have both spins integrated out. We just have one set of electrons with its native spin and the other set of electrons with its native spin. And then we look for a solution. And actually what we're getting is, well, a little better, but still, go for infinite distance and we have infinite energy. Still wrong. Why? Because we still freeze their spin. So our dissociation, here it doesn't matter, here we are. So this is our bonded system, right? Now it doesn't matter. They can have parallel spins before reaction, they can have anti-parallel spins, it doesn't matter. But when we dissociate here, they have to stay anti-parallel. So we're making a mistake. How can we solve it? Well, we can combine the bonding and the anti-bonding wave functions linearly. Right? So what does it mean? This means that in the beginning, when we just have a bonded state, like here, A is 1, B is 0. All is bonded. And if we dissociate, well, in the plus combination, we obtain 2 times, well, with the exception of this 1 by square root of 2, we obtain 2 times phi s1 in coordinates of r1. And in the minus combination, we obtain 2 times phi 1s in coordinates of r2. So A and B are then 0.5. And it works because we are seeing just the average of those. Now, unfortunately, each of these is a single Slater determinant of the system. So now we are not in a single determinant, which Hartree-Fock is, but we are in a multi-determinant situation. And each of these determinants is solved like a Hartree-Fock. Gets a little expensive, right? So, what we are seeing here is close to the minimum. Hartree-Fock yields the correct physical behavior. The state is determined by the dynamic correlation of the electrons, so electrons facing electrons, and seeing the correct mean field. This yields the correct description. So dynamic correlation is what happens with the electrons. Far away from the minimum, Hartree-Fock fails. The multi-determinant wave function yields correct results, okay. So we have a dependence on the distance between the nuclei. But they are static, according to the Born-Oppenheimer approximation with respect to the electrons. So what we have here is static correlation, because it depends on the static part of our electronic Schrödinger equation. In Hartree-Fock methods, obviously, cannot describe static correlation. Well, what can we do about it? Sure, we can go for multi-determinant, right? Nice stuff. Let's say we do it for any system. We have a total spin of S. Let's say all are paired, so we have a total spin of 0. Makes things easier. We have n correlated electrons and n correlated orbitals, which is typically all electrons, all orbitals, unless we have some symmetry constraints. Then we obtain this, and these are binomial coefficients. So let's go up in size, right? Let's say twice as much electrons as correlated orbitals, and we have a pretty mess. Or we can do it even worse and say you also take all of the unoccupied orbitals which we obtain from our solution. Right, go to the lithium example. We have 15 occupied orbitals, but we have 90 orbitals altogether, because the coefficients just don't vanish. I mean, we have a 90 times 90 matrix for our coefficients. So it's still 90 coefficients, 90 eigenfunctions. It's just that all except the first 15 are not occupied. And then it's getting horribly expensive to do this. We don't need so many electrons. Go for 10 electrons with a basis of 6 functions per electron. And compute this, even with a spin of 0. It just goes up extremely. So we actually cannot do this. Especially not when we're working with condensed phasing on top of entire crystals, right? Let us see what we can do about it. Maybe we should not work with the orbitals directly, but rather with the density. And the question is the density really a unique representation of our state? Do we have all the information? To do this, let's consider we have some potential energy, U1. U is the interaction of electrons with electrons, T is the kinetic energy, V is some kind of external potential, which for example is what the potential of the nuclei with respect to the electrons, as we have in chemistry, right? So then we have this energy, correct? Then we have a second potential, also external, with a proper eigenfunction. And if we put this eigenfunction here, so for a variation principle, we know that this eigenfunction with Hamiltonian 1 must yield to a result larger than our energy of the exact solution. Right? Variational principle works, which is then this equation. Now let's look at this from the other side. We have V2, which forms a Hamiltonian H2, and we get an energy E2 of this. It's just the same like this, and the other way around. Now we combine both equations and we obtain that E1 plus E2 must be lower than E1 plus E2, which is obviously not the case. It cannot be. So what we've proven with this is that the density, because what stayed the same is the density. We did not change the density, right? We have the same expression of the density. So if we are having the same density into different functionals, then the density does not describe one of both functionals. So the density is a unique mapping for any external functional. And an external functional is the positions and charges of our nuclei, and perhaps an electric field or something like this. But you're getting the point, right? So the density is a unique representation of our system. This is Hohenberg-Kohn's theory. Hohenberg and Kohn had this already in the 50s, or around 1950 almost. So it's pretty simple. I mean, it's a nice proof. Very simple. So what we have is we need to derive the correct electronic density for any system. Okay, we've solved one problem and have another. Okay, this is our equation for the density, right? And, well, this yields a good approximation, doesn't it? So perhaps we do not need to go directly for the density with anything. So, we are formulating this equation. Kinetic energy of electrons, external potential, which is electrons with respect to nuclei. This one is now expressed in electronic density. This is our Coulomb repulsion of the electrons. Because the density is the mean field, the probability to find all the electrons. So obviously, this is a Coulomb operator. And as we can't be all in the same coordinates, we need to vary our coordinates, of course, a little bit over space. So we integrate over full space. And then we have some exchange and correlation functional, which solely depends on the density. And we still have our basis functions. So it looks like a Schrödinger equation. Right. So what we need to find is, at first, of course, the correct one electron function, so the correct orbitals, and the correct exchange and correlation function. And how we find these, I will tell you in the next session. Because this would be a little bit too much for today. Yeah, so what you see is, I mean, it is really more or less a kind of modified Fock operator, what we have here, and we are expressing something with a density. And the idea is not that stupid, because in Hartree-Fock we already use the density for the prominent row to find out if we are converged. So why not going for the density here as well? And it doesn't matter what kind of basis we have. Neither here nor in Hartree-Fock. It works with a plane wave basis, it works with a Gaussian basis, it works with a Slater basis. As long as the basis is somehow fitting our problem, it doesn't matter what basis we have. We can even go for direct, completely numerical basis, which is only well defined on a certain grid. Doesn't matter, it still works. So, this is the Kohn-Sham equations, because it is for I different basis functions. And yeah, the next session we'll talk a little bit about functionals. But finally we arrived at density functional theory, right? Okay, thanks for your attention.
What does that nu sub x c again? The nu sub x c in the equation.
This is okay. There should be a b, but